Deriving the formula for the conservation of linear momentum. We'll start off with a diagram which shows a standard collision between two masses, mass 1 and mass 2, which are moving with velocities u1 and u2 before the collision, and afterwards v1 and v2. Note that we're going to use velocities only here. I don't particularly like to use speed in these questions. So u1 must be greater than u2 for the collision to occur. Of course u2 could be negative, in which case it would be moved in the opposite direction, but by working with vectors that will all be taken care of within the variable itself. After the collision we know that v1 must be less than v2, and it may well be the case that v1 is in this case negative. If u2 had been negative, it's also technically possible that v2 is also negative, but will be greater than v1. Let's have a look at what actually happens at the time of collision itself. Well, at that time, each of the masses will exert a force on the other mass, and those masses will be equal in magnitude, but they will be opposite in direction, which is a case of Newton's third law. So we can say the magnitude of force 2 is equal to the magnitude of force 1. And of course we could also go on to say that in fact, because these are vector quantities, that F2 would be equal to minus F of 1. In other words, if F1 was minus 10 newtons, then F2 would simply be 10 newtons. Well, let's use Newton's second law. If we first of all look at force 1, then we can say that force 1 is equal to mass 1 times acceleration. Now we know that in fact F1 is going to be negative, but we don't put minus F1 down here, not when using Newton's second law. The reality is the acceleration here will actually be negative, it will be a deceleration, but that again is all taken care of by the fact we're using vector quantities. So if we go ahead a little bit further, we know that the acceleration, considered to be a constant acceleration, will be the change in velocity over the time that it takes for that to occur. So we end up with this expression here. You could also look at this as using a Suvat equation, v equals u plus at, and rearranging it, but that should be fairly obvious. Likewise then for force 2, we end up with a very similar expression. We're now going to use the part where the asterisk is by, and that tells me that F2 is equal to minus F1. So I can create the following relationship just by substituting in the parts we found. And that is really just a case of expanding the brackets and rearranging a little. The t's will cancel, they're just the time for which the impact occurs, or for the duration of the impact I should say. And rearranging, expanding, rearranging gives us the familiar formulae which we know as the conservation of linear momentum. You should understand this derivation, you should be able to derive this should the need ever arise. Now there's a little something else that comes out of this, and so what we're going to have a look at now is just the idea of an impulse. And an impulse is defined as being a force times by the time for which that force is acting. So if I just rewrite a couple of the formulae from the previous slide, we'll notice that in each of these cases I could multiply throughout by t, which will lead to the impulse 1 is force 1 times time, which would be m1 v1 minus m1 u1, and likewise impulse 2 f2t equals m2 v2 minus m2 u2. We might get a question based on this in the exam in one of two ways. It might be a very, very straightforward example where everything just takes place along one straight line, but this form is also perfectly valid in either 2 or 3 directions as well, in which case our impulse would be a vector, our velocities would also be vectors. We'll see an example of that shortly. So we've got that impulse in fact, which is force times time, is equal to the change in momentum that one of the particles exhibits. So what do we see? M1 and M2, they receive impulses of the same magnitude. but they're simply in opposite directions, in the directions of the forces acting on the masses. And if we're ever asked to find the impulse, what we do is we choose either of the masses in the collision, and we then simply use the m, u and v for that mass and work out what the impulse would be.